Hi, everyone. I hope that you are well. Wherever you're tuning in from, I want to extend a warm welcome to you to this lecture series. We've now reached chapter 4 of the textbook Applied Statistics, Business and Management Research, in which we will learn a bit about the normal curve. So just a brief recap. In chapter 1, we talked about the quantitative research process in general terms. And in the second chapter, we looked at the SPSS environment, the graphical interface of the statistical software that we're using in this class to carry out our statistical tests. And in the previous chapter, in chapter 3, we looked at basic descriptive statistics, including measures of central tendency and measures of dispersion, as well as graphical representations of data. This is chapter 4, where we will be learning about the principle of statistical inference. This is the mechanism, the theoretical mechanism that we use in order to generalize the results from our samples to our populations. Okay, without further ado, let's begin. Here you can see the textbook that we are using in this lecture series. It's called Applied Statistics, Business and Management. I've heard that it's a pretty good textbook, but then again, I wrote it, so maybe they were just telling me that so that I wouldn't feel bad. But nevertheless, I feel like it's a pretty good textbook, which is why I'm teaching this course and which is why I wrote it in the first place. Feel free to get the textbook, or if you prefer, you can get it for free by visiting your local university library. You might recall from chapter 1 that we looked very briefly at the process of sampling. Now, the reason data scientists use samples is that we often don't have the resources at our disposal to analyze entire populations. Oftentimes, sometimes we do have those resources. For example, a census, a national census, offers population level data where everyone in the population contributes to it. But for the most part, we don't have the time or the resources to collect data from everyone. And so what we do is we take a sample from that population, and then we run our statistical analyses on that sample, and then we try to generalize the results of those analyses, which are derived from the sample, to the population. So it follows logically that when we're sampling, ideally we want our samples to look and behave as much as possible like the wider population from which the sample was drawn. And the best way to ensure that this is the case is to use random sampling, right? So random samples are generally preferable to non-random samples because random samples tend to look and behave more like the population from which they are drawn. So what do I mean by random samples? If you go out onto the street and you randomly pick people to fill out a survey, pick people to fill out a questionnaire, that would not constitute a random sample. Maybe you feel like it's random, but it's really not. There may be certain people who pass you by that you don't want to approach for one reason, or you're attracted to other people for whatever reason. So a random sample is one in which everyone in the population has an equal probability of selection into the sample, right? And if everyone has an equal probability of selection into the sample, then the laws of probability tell us that the sample is very likely to be representative of the population. So in a non-random sample where everyone doesn't have an equal probability of selection, then we can generally be suspicious of the extent to which our results from the sample generalize to the population. So ultimately, representative samples allow us to generalize our results from the sample to the water population. So how exactly can we generalize our results from a sample to a population when we have perfect information about our sample, but imperfect information about our population? The way we do this is through what we call the principle of statistical inference. So the principle of statistical inference enables data scientists like us to make a quantum leap from the sample to the population. Now, it's important to bear in mind that a sample will never perfectly look and behave like the population. There will always be some deviation, some demographic differences between the sample and the population. But if the sample is randomly drawn, that is to say, if everyone in the sample has an equal probability of being selected into it, then we can mathematically calculate the likelihood that it is representative, the likelihood that the results of our sample will generalize to the population. And the way in which we calculate this mathematically is through something called the normal curve. It's also sometimes referred to as the bell curve. So the normal curve is the theoretical mechanism that we use to enable statistical inference in parametric statistical tests. So inference, just to reiterate, refers to the ability of the statistician to generalize from a sample to a population. Let's talk a bit about this so-called normal curve, this bell curve. It has important and standardized features that allow us to generalize, not perfectly to the population, but to generalize with a specific and reasonably precise degree of confidence. So we have a definition here at the top of the slide. It's important that you understand this definition. So I define the normal curve as a mathematically defined and naturally occurring distribution of scores that appears bell-shaped, right? I should say mostly naturally occurring. As we'll talk about briefly here, no distribution is ever perfectly normal. But generally speaking, you do see in nature, whether in the social world or the natural world, bell-shaped distributions in ordinal or scale level variables. Again, the normal curve is purely hypothetical, right? No distribution of scores, whether you're looking at sample data or population data, is ever perfectly normally distributed. It is an ideal to which we hold ourselves when we make generalizations from a sample to a population, but no real life data ever corresponds perfectly to a normal curve. So what makes the normal curve normal? First of all, it suffers from no skewness or kurtosis. So we talked in the previous lecture about these two concepts. Skewness means that a distribution is dragged to the right by extremely high scores or to the left by extremely low scores. And kurtosis means that a distribution is excessively peaked or excessively flat. A normal curve looks like a perfect bell. It suffers from no skewness nor kurtosis. Also in a normal curve, the mean and the median are the exact same number. This should make sense in light of what I just said about the fact that there's no skewness. So when there is skewness, when there are extreme scores, you will see the mean being dragged either to the right of the median or to the left. But in a perfect normal curve, these scores are identical. And lastly, standard deviation. So this is a measure of dispersion or a measure of the extent to which scores are spread around the mean, are geographically defined vis-a-vis the mean. Now, this is a bit of a difficult concept to grasp, so let's spend a little bit more time on it. Now, there is something you could call natural about the normal curve. And the reason there's something natural is that it just tends to appear in social and natural phenomena across the world. It is a natural shape specifically of many ordinal or scale level variables, right? It tends to emerge organically whenever we try to measure something that is hierarchical. Not exclusively, of course, there are exceptions of naturally non-normal distributions, but in many types of ordinal and scale level variables, the steady state, so to speak, is a bell curve. So what makes it natural? What makes it appear natural? In a normal distribution, in a normal curve, you will typically find the majority of cases centered around the mean. So the majority of cases are typical or average. And as you move either to the right of the mean or to the left of the mean on the distribution, you will find fewer and fewer cases at the extreme ends, at the tails of the distribution, right? And the further you get from the mean, the more rare that type of score is. Again, that's true on both sides of the distribution. So you can think of this, again, with any number of natural variables. For example, height, right? Most people are of average height. There are a few people who are very, very tall and a few people who are very, very short. But for the most part, we tend to cluster around the mean. And this is true of different populations. It's true of men, it's true of women. So that's a case in the natural world where a normal curve just tends to emerge organically. Another example in the sort of social world is IQ, right? So IQ is one of the most normally distributed variables. Most people, the majority of people, will score around 100. That is to say, they have average intelligence. But as you move to the tails, you will see that far fewer people score very, very high, right? Very intelligent, or very, very low on the test. So this is another example of the way in which these bell curves tend to emerge naturally. Now you'll recall earlier that I said that the normal curve is mathematically defined and that our knowledge of the geography of the normal curve is what enables us to make that quantum leap from the sample to our population. This is a bit of a difficult concept to grasp, but I'll do my best to explain it as best I can. So what you see in front of you is a normal distribution. Again, this is a hypothetical distribution. There's no distribution that perfectly corresponds to this type of geography, but it is a generally accepted normal distribution that we use in order to enable generalization from a sample to a population. And you'll recall that one of the key features of a normal curve is that the mean and the median are the exact same number. You can see that they're in the very center of the distribution. The mean and the median are the same. And as you move to the right, you can see one standard deviation to the right, one an additional standard deviation, that's 2 standard deviations to the right, and 3 standard deviations to the right. So 3 standard deviations is obviously higher than 2, which in turn is higher than 1. And what these mean is that the further you get from the mean, the fewer the cases in this particular distribution of scores. So if you think of a y-axis here on this graphical representation, you can see that the tails are far lower on the extremes than they are at the mean. And the tip, the top of the normal curve, is the highest frequency. And the same is true of the left. So when you move from the mean to the left, you go 1 standard deviation down, 2 standard deviations down, and 3 standard deviations down. So the further you get from the mean, the more rare those types of cases are. And you can see here, if you look at the 3 arrowed lines at the bottom of this distribution, that we understand geographically and mathematically that 68.26% of cases in a perfectly normally distributed variable will fall within -1 standard deviation and +1 standard deviation. And we know that 95.44% of cases in a normally distributed variable will fall between -2 standard deviations and +2 standard deviations. And finally, we know that 99.72% of cases in a normally distributed variable will fall within -3 standard deviations and +3 standard deviations. So that even allows for the fact that there may be, for example, someone like Einstein who may be more than 3 standard deviations above the mean in terms of intelligence. So we're thinking about this curve now in terms of IQ. But for the most part, 99.72% of people will fall within -3 and +3 standard deviations. Okay, let's summarize the key features of a normal distribution of scores, of a normal or a bell curve. First point, the mean and the median are the exact same number in a normal curve. If there were skewness introduced into the distribution of scores, then you would find that the mean would deviate either to the right in the case of extreme high scores or to the left in the case of extreme low scores vis-a-vis the median. So correspondingly, it makes sense that skewness would equal 0 in a perfectly normal curve. That is to say that the curve is perfectly symmetrical on each side, to the right and to the left. If you were to flip it along the mean, you would find that the tails are identical. Equally, there is no kurtosis in a perfectly normal curve. In other words, the curve is not too peaked, it's not too tall with too many cases clustered around the mean, but it's also not too flat with cases very far from the mean on both sides. So it still creates a perfectly normal looking curve. And as I said, we can extrapolate in terms of geography the number of cases in a distribution that fall within the geographical features of this bell curve. So within -1 and +1 standard deviation from the mean, 68.26% of cases can be found there. So most people, the majority, about 2/3 of people, fall within -1 and +1 standard deviation. When we extend that to -2 and +2 standard deviations from the mean, we get an even bigger number. So 95.44% of all cases fall within a distribution, fall within the standard deviations in that distribution. And lastly, if we expand to -3 and +3 standard deviations, we can assume that roughly 99.72% of all cases fall within that range. Okay, thank you very much, everyone, for taking the time to listen to this lecture on the normal curve. We will extend this lecture series in Chapter 4, Lecture 2, and I look forward very much to seeing you then. Thanks, everyone. Have a good day. Bye-bye.